Here we're going to give a qualitative introduction to ternary phase diagrams. We're going to use these two very nice diagrams from the textbook by John Winter. We'll start with this one on the left and then show how it relates to this fellow over here. So he's going to take the ternary of anorthite plus diopside plus forsterite. So let's say we have rocks where any or all three of these crystals might form to the exclusion of others. So what we would have is a diagram that looks like this, where we have, let's put diopside down here, bottom left, forsterite bottom right, and then way up here at the top, he's showing up here, but it's really kind of a projection of this fellow here. There's anorthite. So diopside, anorthite, forsterite, we're looking at this surface down here. Let's take a look at this part here, anorthite diopside. We have already seen that diopside anorthite binary in another video. So in that video, when we talked about that binary phase diagram, we mean this part here where we have mixing of anorthite and diopside and no forsterite is involved. And you might remember that that has a eutectic relationship shown by this pink curve, and there is the binary eutectic there. We can draw a line that goes through that eutectic point, and then you can think of the face that's shown here in pink with orange and blue edges is representing that diopside anorthite binary eutectic. Well, what's being implied here is that if we did the same kind of experiments that were done to develop that binary eutectic, that if we did the same thing but instead had anorthite and forsterite, that we'd also end up with a eutectic, but that eutectic would be perched up here at a much higher temperature. And then our diagram's getting a little bit messy, but if just take a look at the blue lines here in front. If we had diopside and forsterite, take a look at these blue lines, we would have another eutectic, also perched at a somewhat higher temperature and shifted much more strongly to the diopside side of the system compared to anorthite diopside, which is close to the middle. So what we're doing is we have temperature increasing upwards, and we're simply going to take these contours of temperature and project them down onto this surface here. So if we did that, we would get curves that look like this. We would take these contours here of temperature, project them downwards. We'd have another surface here. Getting a little bit messy, but that's why we have this diagram over here to the right. So this diagram to the right shows that projection. We have the contours that are shown here, going from pure forsterite melting, which happens at a temperature of 1890 degrees, and we just project that down onto this triangle down here at the bottom. We have anorthite melting at 1553. That's here, and that temperature is being projected down here to the bottom. Diopside at 1392 there. And we'll take that temperature and project it down. And then we have contours such as this. So let's say this fellow here is the 1800 degree contour, and it would be that contour right there, just projecting that contour line down onto that surface. So it's really like a topographic map, except here we are mapping the elevations of temperature instead of elevation. So that's what we have here in this ternary diagram. It is a topographic map of sorts, or rather more strictly a ternary phase diagram that shows the relationships between diopside, forsterite, and anorthite, their crystallization temperatures when they occur as mixtures, when all three phases are possibly present. And then there is a ternary eutectic here that occurs at 1270 degrees, and that's this part M, where these eutectic curves are shown here in green. So here's the eutectic we looked at in another diagram. If we had forsterite, that eutectic decreases in temperature. And then we have this eutectic here along the diopside forsterite curve. That also decreases in temperature. This eutectic here, as we had diopside, it decreases in temperature. And all three of those curves will intersect right here. We're looking at the intersection of these surfaces. So we've got a surface here and then a surface here. They intersect in a line. That line is referred to as a cotectic. So in this case, since it's the intersection of the anorthite surface and the forsterite surface, that would be the cotectic of forstrite plus anorthite. And then we'd have another one that's more or less been obliterated by my drawings, but we'd have another two intersections between the diopside part of the curve and the forstrite and anorthite parts of the curves. And they're shown here. So that curve right there is this one right here. And so we've got another two surfaces that are intersecting here and there. And together those lines intersect to a single point M. And M in this case is probably for the minimum. This represents the minimum crystallization or minimum melting temperature, depending on whether you are adding heat or decreasing heat. In another video, we'll take a look at this diagram and how to interpret it. But this is the gist of the geometry of what the meaning of these lines in this kind of diagram.